Hello friends, this is Inertia and today I am going to discuss moment of inertia of areas. The contents of this video will be moment of inertia of integration, moment of inertia of rectangular, triangular, circular and irregular areas, program moment of inertia, radius of gyration, parallel axis theorem, moment of inertia of composite areas. Let me first discuss moment of inertia of integration. Moment of inertia of the x-axis is data at I of x is equals to integration of y square into df, and y is the distance of the elemental strip, elemental rectangular strip from the x-axis, and dA is the area of the strip. Integrating this y square into dA from by imposing the required limits, we get the moment of inertia of the figure. Similarly, I of y is equals to x square into dA. Now let me illustrate moment of inertia by integration through an example by calculating the moment of inertia of rectangular area. And we are required to calculate the moment of inertia at the x-axis passing through the center of the rectangular area. So let us consider a rectangular strip at a distance y from the x-axis. Its thickness is dy and length is b. The area of the strip dA is equals to b into dy. So according to the formula, Ix is equals to integration of y square into dA, which is b into integration of minus h by 2 to h by 2 into y square into dy. So following this integration we get 1 by 12 into b into h cube. The moment of inertia of triangle area. We are required to calculate the moment of inertia of the triangle around the base, which is the x-axis. Let us consider again a strip, rectangular strip at a distance y from the base of thickness dy and length l. The area of the strip dA is equals to l into dy. Using the similar triangles, we can find the value of l. As this smaller and this bigger triangle are similar, we have the relation a by b is equals to h minus y divided by h. From this, we get the value of l, and for finding the moment of inertia about x-axis, we can calculate the integration 0 to h y square into dA is 0 to h y square into b into h minus y by h. And solving this integration, we get b into h cube divided by 12. The polar moment of inertia. Polar moment of inertia is divided by J naught, and it is equal to integration of r square into dA, where r is the distance of the elemental area around the elemental strip from the point under consideration, and dA is the area of that strip or patch. So integrating by r square into dA, we get the polar moment of inertia, and polar moment of inertia is equals to r square into dA. R square is equals to x square plus y square into dA. So polar moment of inertia J naught is equals to Ix plus Iy. Actually, this polar moment of inertia is the moment of inertia about an axis which passes through the point under consideration and which is perpendicular to the area under consideration. Then let us calculate the moment of inertia of circular area. Let us circle a radius r about its centroid, that is about an axis passing through the centroid perpendicular to the area. Let us consider an elemental strip which is circular and of thickness dB, and which is at a distance of d from the origin. we have dA is equals to 2 into pi into b into dv. So J naught is equals to h square into dA, which is b square into dA, and we have to integrate it from 0 in the origin to certain things 0 to r. So we get the integration 2 into pi 0 to r d cube into dv, which is equals to pi by 2 into r to the power 4. Now let us calculate the moment of inertia with the diameter. So we have the relation J naught is equals to Ix plus Iy. Now let us consider the diameters as the x and y axis, diameters of the circles as x and y axis. As the circles are symmetrical with the diameters, so Ix and Iy will be same. So 2 into Ix is equals to J naught, Ix is equals to pi by 4 into r to the power 4. Radius of gyration. The distance from an axis at which the mass of the body or area of the body may be assumed to be concentrated. So we have Ix, which is the moment of inertia along the x-axis, equals to kx square into a. Kx is the radius of gyration along the x-axis. So we have kx is equals to root under Ix divided by a. A is the area under consideration. Area of the figure under consideration. We have another relation k naught square equals to kx square plus ky square. But k naught square, k naught is the radius of gyration of the polar moment of inertia. The moment of inertia of irregular radius. Find the moment of inertia at y-axis of this figure. The relation between y and x is given. We need to calculate the moment of inertia of this figure about y-axis. So let us consider a rectangular strip at a distance x from the y-axis, and its height is y, and its thickness is dx. So dA, area of this strip, is equals to y into dx. We have y equals to k into x to the power e to the power x by a. So we get dA in terms of x, which is dA equals to k into e to the power x by a into dx. Okay? Solving for Iy, we have Iy is equals to integration of x squared dA, so it is k into 0 to a x squared into e to the power x by a. Solving this, we get this value. Axis theorem. It is used to determine the moment of inertia about any axis parallel to an axis passing through the center of mass. So not we can apply momentum in a parallel axis theorem only when the axis passes through the center of mass. So for applying parallel axis theorem, we need to at first calculate the moment of inertia of the body about an axis which passes through the center of mass of the body. So I equals to I naught plus a into d square, where I is the moment of inertia about required axis, I naught equals to moment of inertia about central axis, a equals to area of the body, and d is technical distance between the axis. Let us apply the parallel axis theorem. Earlier we calculated Ix of the rectangular figure, that is moment of inertia of this figure about the x-axis passing through the center of the rectangle. Now we are required to calculate about an axis x dash which is parallel to the angular axis, and it is at a distance of h by 2 from the angular axis, x-axis. So I naught x dash is equal to 1 by 12 into b into h cube plus b into h, which is a, into h by 2 y square. H by 2 is the d distance between the axis. So we get x dash equals to 1 by 3 into b into h cube. Moment of inertia of composite areas. And let us consider an area of A which is divided into smaller areas of A1, A2, A3, A4, A5. of inertia of this A1 about y-axis is I1. Moment of inertia of A2 about y-axis is I2. Moment of inertia A3 about y-axis is I3. And moment of inertia of A4 about y-axis is I4, and moment of inertia of A5 about y-axis is I5. So for calculating the moment of inertia of the whole body about the y-axis, we have I of y is equals to I of y1 plus I of y2 plus I of y3 plus I of y4 plus I of y5. Let's take by an example. Let us calculate the moment of inertia of this figure around this x-axis. This shaded portion, this field have mass, but these white semicircular portions are hollow. So at first calculate the moment of inertia of the semicircular rod x-axis. And we know the moment of inertia of the semicircular rod is diameter, but we don't know the moment of inertia about its center of mass. We know the moment of inertia about the diameter of the semicircle is pi by 4 into 8 by 4 into 1 by 2. Pi by 4 into 2 by 4 is for a full circle, and as it is a semicircle, we have to multiply 1 by 2 with it. Now, for calculating the moment of inertia about its center of mass, we have to use the parallel axis theorem, and then we have to subtract AB square from the given moment of inertia. So we have minus pi by 2a square, which is the area of the semicircle, into 4 by 3 into a by whole square. This is the length square. This is the distance between the diameter and the center of mass of the semicircle. So now we have the moment of inertia about the center of mass of the semicircle. Now we can apply the parallel axis theorem and find the moment of inertia about the x-axis. So plus pi by 2 into a square, which is the area of the semicircle, into 3 by 2 minus 4 by 3 pi into a whole square, which is the distance, d square. So similarly, we can calculate moment of inertia of circle 2 about the x-axis. These two terms will be the same, only this a d square will vary. I am leaving this as an exercise. Now, for calculating the moment of inertia of this figure, we consider this hollow portions to be filled with plus mass, hypothetical plus mass as well as a minus mass, or plus area as well as a minus area. So plus minus is becoming 0, so it is becoming hollow. So at first, considering the positive areas, we have a whole rectangle. So when we have a whole rectangle, so at least considering the positive areas, we have a whole rectangle. When we have a full whole rectangle, we can use the moment of inertia of the rectangle around this x-axis. So I return I of rectangle. Now consider the negative masses. So it is also composed of two negative masses, the negative areas. So we have one negative area minus I of circle 1 and another negative area minus I of circle 2. So by calculating this I of rectangle minus I of circle 1 minus I of circle 2, we get the moment of inertia of the figure around the x-axis. So like this, we have